Hi friend, welcome all to my educational channel Math A to Z. This is the second class of the power series solution of ordinary differential equation of second order. In this class, we learn the method of power series solution of the second order ordinary differential equation of ordinary point. So we consider a proper example for which the given point is ordinary point. Here the example is power series solution of d2y by dx2 plus x into dy dx plus x square plus 2 into y equal to 0 in powers of x. And from the question it is clear that we have to find out the power series solution about the point x equal to 0. Powers of x means x equal to 0. Now here p of x is x and q of x is equal to x square plus 2. Here both are analytic everywhere. So it is analytic at x equal to 0 because our target is x equal to 0. So x equal to 0 be an ordinary point. Ordinary point of 1. This is 1. Okay. Now we take the power series solution of 1 as we take power series solution of 1 as y equal to summation n equal to 0 to infinity cn x to the power n. This is true. Now we have to find dy dx and d2y by dx2 and put them in this equation. So dy dx is equal to summation n cn x to the power n minus 1, and here the range is n equal to 1 to infinity, because if n equal to 0 then this is not in power series because the power of x is negative, and this is 3 and d2y by dx2 is equal to n equal to 2 to infinity n minus 1 cn x to the power n minus 1. This is 4. Right? Here 1 y dy dx d2y by dx2. Now we put y dy dx and d2y by dx2 in 1 and we get the result as this plus x into summation n equal to 1 to infinity cn into n x to the power n minus 1 plus x square plus 2 into summation n equal to 0 to infinity cn x to the power n is equal to 0. And multiplying by x and multiplying by x square plus 2, we get the result as summation n equal to 2 to infinity n into n minus 1 cn x to the power n minus 2 plus summation n equal to 1 to infinity n cn x to the power n plus summation n equal to 0 to infinity cn x to the power n plus 2 plus 2 into summation n equal to 0 to infinity cn x to the power n equal to 0, and this is 4. 4 is an identity. So we can equate the equal power of x from both sides, and since the right hand side is 0, so we can equate all the coefficient of x from left side is equal to 0. Now the coefficient of x to the power 0 is we get the coefficient of x to the power 0 from here. If we take n equal to 2, then the coefficient is 2 into 2 minus 1 into C2 plus, and here also if we take, no, there is no x to the power 0, and here then also not x to the power 0, and here also x to the power 0. This is 2 into C0 equal to 0. That is 2C2 plus 2C0 equal to 0. That is C2 plus C0 equal to 0, and this is 5. Now the equating the coefficient of x to the power 1, we get, to get x to the power 1, here we put n equal to 3, because n equal to 2 to infinity, so here we get n equal to 3 into 3 minus 1 into C3 plus, here also n equal to 1, then we get x to the power 1, that is 1 into C1, and here if we put n equal to 0, then this is not x to the power 1, and here we put n equal to 1, then we get x to the power 1, that is here also plus 2 into C1, this is equal to 0. That is we get 6C3 equal to minus 3C1, that is here C3 equal to minus half into C1, this is 6. Now to get a recurring relation, we equate the coefficient of x to the power n for n greater equal to 2 from both sides. We get x to the power n. To get x to the power n, we must have to put here n equal to n plus 2, right? Then the coefficient is n plus 2 into n plus 1 into c n plus 2. Here this is n equal to n, so plus n cn, and here is also n equal to n minus 2, right? So this is cn minus 2, and here also n equal to n, that is plus 2 cn, this is equal to 0. So we get the recurring relation as cn plus 2 is equal to minus n plus 2 into cn plus cn minus 2 by n plus 1 into n plus 2 for n greater equal to 2, and this is named as 7. Now if we put here n equal to 2, then we get C4 is equal to minus 4 C2 plus C0 by 12, and we also know that C2 is equal to minus C0, and we put here C0 and we get, this is, now we put C2 from 5, that is C2 equal to minus C0, we get 1/4 into C0. For C5 we put n equal to 3, then C5 is equal to minus 5 into C3 plus C1 by 20. Also we get C3 equal to minus half into C1, that is we get, this result becomes 3/40 into C1, and so on. We put the value of C0, C1, C2, C3, C4, C5 in the solution, that is y equal to summation Cn x to the power n equal to 0 to infinity. We get the solution of 1 as y equal to C0 plus C1x plus C2x square plus C3x cube plus C4x to the power 4 plus C5x to the power 5 plus to infinity. And here C0 is remains C0, C1 is remains C1 because all the value we can find either in terms of C0 or either in terms of C1. So C0 plus C1x plus, here we put C2, the value of C2 is minus C0 x square, and value of C3 is minus half C1 x cube plus C4 is 1/4 x to the power 4, C5 is 3 by 40 into C1 x to the power 5 to infinity. Y equal to C0 into 1 minus x square here is C0 plus 1/4 into x to the power 4 to infinity plus C1 into, this is x minus x cube by 2 plus 3 by 40 into x to the power 5 to infinity, and this is CA into u of x plus b into v of x. This is u of x and this is v of x, and u of x and v of x are two linearly independent solutions of the differential equation 1, and this is the complete solution of 1. Okay, this procedure is for the ordinary point, solution about the or solution near the ordinary point. Now we go to the another example. Power series solution of the initial value problem x y double dot plus y dot plus 2y equal to 0, where the initial conditions are y of 1 equal to 1 and y dash 1 equal to 2. Since here the initial value is given for x equal to 1, because y of x equal to 1, that is x equal to 1 here, also x equal to 1 here. So we have to find the solution near x equal to 1. Okay, now we check x equal to 1 is either ordinary point or singular point of the equation 1. Clearly here p of x is equal to 1 by x and q of x is equal to 2 by x. So both p of x and q of x are analytic at x equal to 1. So the x equal to 1 is an ordinary point of the differential equation 1. So the solution, we can take the solution of 1 as y equal to summation n equal to 0 to infinity Cn x minus 1 whole to the power, because this solution is taken near x equal to 1. This is the taken solution and this is 2. Now we differentiate this, get y dash, and double differentiate this, we get y double dash. This is y dash is equal to summation n equal to 1 to infinity n Cn, and this is 3, and y double dash is equal to So from 2 we get y dash, this is equal to this. Here the range is from n equal to 1 and y double dash range start from n equal to 2. Now putting the value of y dash and y double dash in 1 we get. Now putting the value of y dash and y double dash in 1 we get the result as this is 5. Now equating the coefficient of x minus 1 to the power 0 from both sides, since it is an identity, and we get here x to the power x minus 1 to the power 0, that means n equal to 0. So here n not equal to 0 because here n start from 2, and here if we put n equal to 2, then we get x minus 1 to the power 0, that is 2 into 2 minus 1 into C2, and from here we get x minus 1 to the power 0. If we put n equal to 1, that is C1. Also here if we put n equal to 0, then we get x minus 1 to the power 0. So here from 2 C0, this is equal to 0, and this gives C2 equal to minus C1 plus 2 C0 by 2, right, and this is 6. Now to get the recurring relation, we equate the coefficient of x minus 1 whole to the power n from both sides, where n greater or equal to 1, and we get from here, if we take x to the power n, then we have to put n equal to n plus 1, and this gives n plus 1 into n into cn plus 1. Here we have to put n equal to n plus 2, that is we get n plus 2 into n plus 1 into cn plus 2. From here we get n plus 1 into cn plus 1, and from here we get 2 cn, this is equal to 0, and from this relation we get cn plus 2 is equal to minus n plus 1 whole square into cn plus 1 plus 2 cn by n plus 1 into n plus 2, and this is for n greater or equal to 1, and this is 7. From 2, that is y equal to C0 plus C1 x minus 1 to the power 1, C2 x minus 1 to the power 2, C3 x minus 1 to the power 3 to infinity. Here the initial condition is y of 1 equal to 1, that is y equal to 1 when x equal to 1, and putting the value of x equal to 1, y equal to 1, we get 1 equal to C0, that is we get the value of C0 is equal to 1, and from 3, that is differentiating them, we get y dash equal to C1 plus 2 C2 x minus 1 plus 3 C3 x minus 1 whole square plus 2 infinity. Here we put x equal to 1 and y dash equal to 2, that is 2 equal to C1. So we get C0 equal to 1 and C1 equal to 2. Now we put C2 equal to minus 2, and then from the value of C0, C1 and C2. From C0, C1 and C2, we get the value of C3 by putting n equal to 1. C3 equal to minus 4 C2 plus 2 C1 by, this is 2, this is 3, that is 6. And putting the value of C1, C2, we get the value 2/3, 2/3. Okay. Similarly, C4, by putting n equal to 2, we get the C4 as minus 1/6. C5, 1/15, and so on. We put the value of C0, C1, C2, C3, C4, C5 and so on in 2. We get the complete solution as y equal to C0 means 1 plus C1 means 2 into x minus 1 plus C2 means minus 2. This is minus 2 into x minus 1 whole square plus C3. C3 means 2/3 into x minus 1 whole cube. C4, this is 1/6 into x minus 1 whole to the power 4 plus 1/15 into x minus 1 whole to the power 5 and so on. And this is the complete solution of the given initial value problem. Okay, so this is the second class of the series solution. Now come back soon with the third class. Thank you very much.